Okay, let's just review. Usually circular motion and gravitation, they combine together because they are two related questions. And this will be the first question usually. We have a circle or circular path, center C, there's a center there. And then there's the mass moving in a circular path. Body of mass M. That's the speed of the object. And then the radius of the circle is R. Center is C. This is your angular velocity. To find the speed, we use distance over time. So if our distance is the circumference, then the time is the period. Right? This is called linear speed or tangential speed. And then there's the centripetal acceleration, centripetal force. You have to memorize it and know how to use both of them. Centripetal acceleration v square over r or r omega square. And then angle, we don't call it angle, we give it a special name, angular displacement. Right? The term displacement shows that it's a vector quantity, either clockwise or anti-clockwise. Then we got angular velocity. Right? We define it as theta over t or d theta dt. And then if you go one round, same. One round, theta will be 2 pi radian. T will be the period. Right? Know how you derive it. And know how to use the equation. And then V equals to R omega. Know how to use this equation also. Remember, the centripetal force is a resultant force acting on a body. If the body of mass M is moving a circle of radius R, then we can say that has a centripetal force or centripetal acceleration acting on it, and the direction is towards the center. Right, so condition for circular motion will be force is always constant in magnitude and perpendicular to velocity. These are the two conditions. Right, we started off with a gravitational field. And then the first thing we remember, I think, let us watch the video first, then we'll go over it again. No. Can you hear the sound?
It's quite like.
Oh, sorry, my fault.
Quickly place two large masses next to the mass of the scale. If you wait and observe, you can see the
Can you hear now?
Yeah, I can.
Okay.
two small masses will move closer to the masses, and eventually they will stick together. This force of attraction happens due to the gravitational force. It looks interesting, right? Let's learn a few more details about the universal law of gravitation and how Sir Newton discovered this very important law. As we all know the story, an apple fell down from a tree, which started Newton. Let's assume there is one more apple tree that is far away from the current tree, and an apple falls from it as well, as shown. If you analyze this way, it is clear that objects fall to the Earth in a radial direction, or the Earth attracts the objects radially towards the center. This observation was the turning point in the discovery of the universal law of gravitation. Newton realized that the Earth does not attract the objects just down, but it attracts the objects radially towards its center. It's logical to conclude that, in a similar way, the Earth is pulling the Moon radially towards its center with an attractive force. Similarly, the Sun as well is attracting the Earth towards its center with a certain force. Now let's move away from these rounded objects. With the same logic, this car will attract this book towards its center of mass. Similarly, this book will attract this car towards its center of mass with a certain force. According to Newton's third law of motion, these two force values should be equal. In short, all the objects in the universe attract each other with a certain force. This is the universal law of gravitation. Now, the next challenge. Newton wanted to derive an equation to predict the magnitude of the force which arises due to the universal law of gravitation. Newton's intuition told him that the effect of gravitational force would dilute with distance. But to what extent? To get an answer for this question, he looked at the Moon. The Moon is also attracted to the Earth due to the same gravitational force. However, the Moon doesn't fall to the Earth because the centripetal force required for the Moon's circular motion is supplied by the gravitational force. People at that time already knew the Moon's angular speed and the distance between the Earth to Moon. Based on this force balance idea, Newton calculated the centripetal acceleration of the Moon. The force acting on the apple near to the Earth's surface can be easily calculated by measuring the apple's acceleration. The value of this acceleration is 9.81 meter per second squared. Newton compared these two acceleration values with the distances from the center of Earth. Can you spot any connection between these four numbers? If so, congratulations! Anyway, Newton was able to find out a definite connection between these four numbers. Divide the acceleration values. Now, take the square of the distances and divide. Surprise! The resultant values are very close. This means the gravitational force is inversely proportional to the square of the distance between the center of the objects. What a brilliant deduction! The next question is, do the objects' respective masses have any connection with gravitational force between them? Newton had already derived the equation for an object's acceleration during this period, and it is a common observation that when the force arises due to gravity, the value of acceleration does not change based on an object's mass. Therefore, the value of force due to the universal law of gravitation should be a factor of the mass, so that when you find out the acceleration by dividing the mass factor will get cancelled. Likewise, we have to include the mass of the second object as well in this equation, in this case, the Earth's mass. This is the expression Newton derived to find out the force due to the universal law of gravitation. He introduced a constant called the gravitational constant and made it a proper equation. According to the universal law of gravitation, all the objects in this universe attract each other. In this case, the Earth attracts the apple with a force value defined by this equation. The apple also attracts the Earth with the same force value. However, the Earth doesn't move to the apple because when you divide this force by the mass of the Earth, the acceleration value becomes negligible. The case is the same with every other object in the universe. It's somewhat impossible to believe, right? Are all the objects in the universe really attracting each other? We find this idea difficult to believe because we live in a world where frictional force is always present. Just imagine a long, frictionless room with no object in it. Now, introduce two blocks on the floor. If the frictional force between the object and floor is zero, you would see the blocks move toward each other due to the gravitational force and finally collide. Of course, this was a hypothetical experiment. A more realistic experiment to visualize the effect of gravitational force would be placing two heavy balls near a hanging two-ball arrangement. If no objects are near them, you'd observe that slowly the small balls would move to touch the larger ones. Even though Sir Isaac Newton derived equation for the universal gravitation, he didn't find a value of g. Many years later, an English scientist named Henry Cavendish came up with a clever idea to determine the value of g. His experiment was very similar to the example we saw earlier. The only difference is that his setup was able to attain a balance force between the force due to gravity and the string's torsional force. You can see clearly that when the torque produced by the torsion of the spring is the same as the torque due to the gravitational attraction force, the balls balance. Using this twisted angle at the balance as an input, Cavendish calculated the value of g for the first time, that too quite accurately. We hope you now have a clear understanding about the universal law of gravitation. See you next time.
Did you know that the most dangerous prayer you can ever pray is only 3 words? If you skip this healing prayer,
Okay, let's just go back to our lecture. Review what we have learned so that you refresh your memory. Right? We started a point mass outside a uniform sphere. Right? A point outside a uniform sphere. Uniform sphere would be uniform density lah. Mass of the sphere may be considered to be a point mass at center. So if it's a uniform sphere, we can consider the mass is concentrated at its center. And then we introduce the term, right? Any object has a field around it, or any body has a field around it. How do we measure the field? Like for the Earth, right? It has a gravitational field G. Near the surface of the Earth is parallel because it's uniform. So we want to measure G. We find the mass using a top end balance, and then find the force. We can measure using a spring balance, and then divide that. Gravitational field strength is force per unit mass. Okay, or sometimes we can think it of acceleration due to gravity lah, same thing lah. But here we are more interested in call it gravitational field strength. Then we came to forces between point masses, Newton's universal law, right? F equals to G mm over r square. That is given in your data sheet. The constant G. So F is the gravitational force. And how do we know it's called a point mass? Remember the distance between the two masses is greater than usually we call it size rather than diameter because it can be any, doesn't have to be a sphere. Then we study motion of satellite. Right? That's the Earth. That's the orbit of the satellite. And we say that for the satellite, it can be a satellite or it can be the moon moving around the Earth. So gravitational force provide a centripetal force. Or usually examiner will prefer you to write out centripetal force equals gravitational force. That's usually 1 mark lah. Then we derive this equation, v square equals to gm over r. R is the radius of the orbit. Then after that, we are going to replace that v with 2 pi r over t. Right? Show t square equals r. T square is proportional to r cube. This one is Kepler's law lah. This is experimental law. Whereas when we derive t square over r cube, we are basically using Newton's universal law of gravitation. So it confirmed to us that Newton's law of gravitation is correct lah. Then we look at geostationary orbit. Then after that, we will look at field of a point mass. G equals gm over r square. Or we can call that acceleration due to gravity lah. But we will call it field of a point mass. the mass of the point mass is m. Distance r away from the point mass. And finally, hopefully we can cover gravitational potential lah. Okay, motion of satellite in circular orbit. Right? Well, we can consider, if you like, this is your Earth. Right? Body of mass m, capital M. Then orbit, this is the orbit of the satellite. Radius of the orbit is r. Mass of satellite m. If one can think of this as the Earth, this as a satellite, artificial satellite, or if one can think of a moon also can, not different. To have a speed, or it has a direction, so it's a velocity, and the centripetal force is acting towards the center of the mass m, capital M. Right? That's the centripetal force. So centripetal force is provided by the gravitational force of the body on the satellite. Assuming the body of uniform density, these two mass of uniform density, or they are far apart from each other, so we can call it point mass. Motion of satellite in circular orbit, right? Gravitational force equals centripetal force. So gravitational force is G m over r square. And then that is your centripetal force, mv square over r. Cancel the small m. Cancel the radius. You got v square over gm over r. Right? So in the formula, we can see that mass there is not in the formula, not in the equation. So it means that it doesn't matter about the mass of the satellite. It can be very large, can be very small. As long as you want the speed, it's governed by the mass of the Earth and the radius of the orbit. Mass of the satellite doesn't come in. Right? So it does not depend on the mass of the satellite. It can be any mass there. Okay, so we have derived this equation. We square root it, we get Gm over R. Right? That's the mass of the Earth, the mass of the satellite, M. That's the radius of the orbit. The equation allows us to calculate the speed at which satellite must travel to stay in a circular orbit. So that speed for a particular orbit only, R. Mass of satellite is not in the equation. Right? As we have gone over, mass of satellite, small m, is not in the equation. So it tells us that the speed doesn't depend on the mass of satellite. Speed of satellite decreases as the radius of the orbit increases. So as you move R orbit further and further away, the speed of satellite decreases. As you move it closer, R becomes smaller, the speed increases. Right, now we are going to derive the relationship between T and R. T is a period. Same. Capital mass M, small mass. Example, the moon, small mass. That's why we have derived the equation. Now we replace our V equals to 2 pi R over T. Square it. 4 pi square R square T square GMR. Take R across, it's R cubed. Take 4 pi square down. Right? GM 4 pi square is constant. Right? It's quite a popular question, come out quite often, either deriving this one or deriving this equation, or they may play with you lah. Introduce density inside this equation lah. Okay, so you must be able to play with them lah. Okay, so we can apply this equation that we have derived, R cubed over T square, from Newton's universal law of gravitation. Now we can go and compare. Is it true or not? Right? So experimental result, Derivation tells us r cubed over t squared is a constant. This expression was obtained experimentally by Kepler. So Kepler has shown earlier r cubed over t squared is a constant, and it's called Kepler's third law. So Newton's universal law of gravitation verify Kepler's observation. Right? This one just for your info only. You can see that r cubed over t squared is roughly constant, right? Different by 0.01. Okay, what is the kinetic energy of the satellite in terms of m, and r? Right? What's the kinetic energy formula? R mv squared for the satellite, right? And then that is what we have derived. Replace that v with that v there. So we get gm over 2r. Okay, any comment so far?
Okay.
Okay, then we can carry on. Okay, try this question. A moon takes 28.25 days to make a complete orbit around the Earth. The orbit is a circle of radius 60 times the equatorial radius of the Earth. Calculate the speed of the moon. Radius of the Earth is given 6400 kilometer. How to calculate the speed of the moon? Use the formula, right?
V equals 2 pi r over t.
That's right. Convert your 28.25 days to second, times 24 hours, and 3,600 seconds. Get that equation for the period. Then use your equation that you suggest, 2 pi r over t. Put inside the equation, calculate out 989 meter per second. How to calculate the mass of the Earth? Use our equation that we derived just now, v square. Right? V square equals gm over r. R is the radius of the orbit. Put in the equation. Right? That's the speed that we have derived. We have calculated. Right? That's the radius of the Earth. 60 times 60. That's your 60 times. And then G is 6.67 times 10 to the 1 is 11. That's the mass of the Earth that we want. Okay. About 6 times 10 to the power 24 kilogram. Anything that is not clear?
Okay.
Observing the Earth. Artificial satellites have a variety of uses. Normal in the syllabus, it used to have communication, telecommunication, but normal in the syllabus already, they have changed it. Many are used for making observation of the Earth's surface for commercial, environmental, meteorological, and military purposes. Spying on a country, see whether they have built nuclear power station or nuclear bomb. Others are used for astronomical observations, benefiting greatly from being above the Earth's surface. They can observe the stars using satellite. Others are used for navigation, telecommunication, and broadcasting. Right? Region of coverage by satellite. One satellite will cover about 1/3 of the Earth surface. So you need 3 satellites to cover the whole Earth. Geostationary orbit. Other name, geosynchronous orbit, parking orbit. Parking orbit is not that common, only used by Nelson and Parker. The reason why it's used parking is like parking a car. When you park a car, the car stays there. So when you park your satellite, in a parking orbit or geosynchronous orbit, it stays there above the same point all the time. In geostationary orbit, the satellite move in equatorial orbit. It must be equator. The orbit must be at the equator with a period of 24 hours, same as the rotation of the Earth, 24 hours, and move from west to east. Okay, three conditions. Satellite remains directly above the same point, above the Earth's surface throughout its life. How memory works. In this orbit, the satellite orbits the Earth at the same rate as the Earth. Right? Same angular velocity. That's what I mean by same rate. The satellite orbits the Earth with the same period, either same rate or same period, same angular velocity or same period, same thing. Right? So these are the conditions. From west to east, direction of the Earth's rotation, period of 24 hours, orbit above the equator. That's for geostationary orbit. Motion of satellite, polar orbit. Polar orbit is 670 kilometers from pole to pole nearer. Geostationary orbit are a lot further away from the surface. So it means that you have to boost the energy, and you have to boost the signal received from the satellite. Right? So this summarize for you what are being used. Right? Okay, we've completed that. Now let's go to field of a point mass. Okay, in case we got cut off, we got 10 more minutes. Try the question. Field of a point mass for a spherical body of uniform density and mass m, that's a body, center C, radius r, mass m. The gravitational field strength at a point P at a distance r away, that's your point P, a distance small r away from the center, is gm over r squared. Okay, so we want to determine the gravitational field strength of this point mass, at a distance r away. Right? Force on, so usually we put a test mass there. Test mass there is placed a distance r away from the point mass in the field. Right? That's a test mass. Right? That's what we started with. Gravitational field, we want to measure the field strength. We put a test mass there, m, a distance r away, and the point mass will attract the test mass with a force F. Right? So that force is given by G, Newton's universal law of gravitation. F equals to G mm over r squared. Right? Product of the mass, distance apart, r squared. And from definition of G, right, we define our G as this force divided by this mass. Put this equation into here to replace F over m, more m cancel off. So you need to memorize this equation in order to derive. Right? Remember, the field surrounds the body. It goes to infinity. So to know there's a field, we put a test mass there. The test mass will be attracted to the point mass. So we know the test mass is in the gravitational field of the point mass. Right? The test mass there, just to review what we have just done, we place a test mass, m, a distance r away, determine the force on the test mass, then use the definition to find the gravitational field strength. G is F over m. For the Earth, right, all these lines are gravity line of force pointing towards the center, same like electric field. Right? We are using the same idea as electric field. At the surface, the lines are radial. Right? These are radial. That means all following the radius towards the center of the Earth. For large distance away from the surface of the as you go away from this equation, we see that as r increases, your g decreases. Right? Remember, g can be called gravitational field strength or acceleration due to gravity. Same thing. But we are more interested to call it gravitational field strength. The Earth has a large radius, so for height h above the surface that is small compared to its radius, the lines are approximately parallel. Right? Small surface above the Earth, the lines are roughly parallel, so it's uniform field. So usually they will give you radius of the Earth and the altitude or height above the surface. Right? Radius of the Earth is about 6.4 × 10⁶ meter. So within the height of 2 kilometer or even 3 kilometer, the gravitational field strength of the Earth is uniform, constant, parallel. Right? For radius of the Earth, 6.4 × 10⁶ meter, near the surface of the Earth where the altitude h is less than 2 kilometer, the gravitational field strength is uniform. Right? That means your h, the height above the surface, is very much less than the radius. Right? Remember, g is a vector quantity, and you must know how to draw the graph. Right? Where you are given radius of the Earth is r, at the surface of the Earth is g0. Right? Complete the table. Right? Gravitational field strength g, there's r, small r, distance away. So at the surface, you are given g0. You don't have to put negative sign if you don't want to. Right? It's up to you. Right? Not necessary. But I put a negative there because it's an attractive force. Right? At the surface, you are given is g0. So at the surface there, we can put our g0 there. Right? And then r, because of r square, you divide by 4. Because of r cube, sorry, 3 square, you divide by 9. So you get 1/9. Right? And then 4 square, you divide by 16. So that's how the graph looks like. Usually you are required to draw one side positive. Don't need to worry about negative sign. Right? The mass involved, we use the equation g or m is constant. Take across there, gr square is a constant because gm is a constant. Right? And g1 r1 square equals g2 r2 square. And when g2, take r2 square down. That's our equation. And put in our r. Right? G1 is g0. Radius, capital R. And this n times r. Cancel capital R. That's how we get the equation. Right? Just memorize the equation and not need to derive it. So if you are 2r away, divide by 2, 2 square. 3r, 3 square. Okay or not?
Yeah.
Right, this is just for your info, how it varies. Earth surface 9.81, 1000 kilometer is 7.33. Right, just for your info only, no need to worry about that. This for info also, similarities between electric and gravitational field. Both are force field. Similarity Both field follow an inverse square law. Inverse square law, it means force is proportional to 1/r square law. The strength is measured as force per unit mass or force per unit charge. Differences. test mass placed in the field will move in the direction of the gravitational field. While a test positive charge, right? When it comes to electric field, you got positive charge and negative charge. So we use positive charge as our guide. So the positive charge will move in the direction of the field. We will study this later on. So the positive charge will accelerate in the direction of the field. Negative charge accelerate in the opposite direction to the field. Okay, that's a pictorial form. Right? Differences. Gravitational field got one mass only, whereas it got positive or negative charge. Positive charge, negative charge, the field lines are different. Gravitational field line always point towards the point mass, while electric field line point away from the positive charge and towards the negative charge. Right? The line point towards the negative charge, point away from the positive charge. Okay, so all these formula you need to know how to use. Okay, let's see whether we got time to try some question.
Joe, can you go up there again? I want to screenshot.
Okay,
I need to screenshot the formula. Slightly down because
cannot move
okay.
already unless can.
Yeah.
Okay, we will get cut off at any time. Let's try this question now. While for the break, you also try the other question, no? Pause on